I'm gonna hit record.
Started
I'm gonna
seeing
get
that in here.
started. It's good to see you guys. Hope you guys are doing well.
Wait, so you want to like erase that before you start?
Erase
Hey
what?
man, leave it in there.
Oh,
Give it
shoot.
some.
Oh my god. It's too late now. All right, whatever. It's okay. They
The
won't.
one time remember to record.
They won't actually watch these. These videos are private. So unless if like you guys share them,
Imagine.
it'd be really messed up. So, but yeah, I hope you guys are doing well. I'm coming off of a meeting that we just had. We meet every week and talk smack about you guys, and
Bruh.
good smack. And yeah, I mean, like, you know what? I just want to say, like, because I know, like, I'm rushing through everything. And we don't really get a lot of chances to kind of actually talk like real. But I just want to say thank you to you guys so far for like being relatively honest with your work. There was word that like the kids in Calc 1 all cheated on the midterm. I don't know if you guys heard about that. I'm sure you have by now probably, but I see you guys nodding. Yes. And I appreciate that you guys at least perform at a standard that is honest. I can tell by the majority of your works that you guys are kind of like putting your effort in, getting like real score. These are real scores, like average before the curve. I don't know if I said this was a 59% on the midterm. And, as as you guys face palm or like, tell yourselves like, oh my gosh, like that's so poopy, right? It's honest. That's what I appreciate, that you guys are actually putting in an honest effort and like, a real effort, because like I said, like we're going through this material so freaking fast. It's normal. It's normal if you're not performing as well as you're like used to. Now, with that being said, I'm grading quiz 2, and they're not coming out so well. The outcomes are very honest so far. I'm like 7 or 8 quizzes in, and yeah, the average is like, I'm seeing like 40s and 50s and 30s and 176 so far, like 176%. But so far, it's like not. So another curve. No, I don't curve the quizzes. The saving graces only come with the exam. So if you guys don't do so well on the final, don't worry, I'll curve that too. So just remember, the final is like worth like what, 25%. The midterm's worth like 20%. Quizzes worth like, I think like 15 or something like that, or 20 or whatever. So don't worry if you don't perform so hot on these quizzes. Like I said, keep doing your best. Do what you can. We're going through this material at an alarming pace. We're going even faster than you would in the fall. So like I said, don't sweat it. It's fine. All right. All right. Oh, did everyone take the quiz? There were, I think I got Alvaro's, but there was someone else. Sorry, can you out yourself? I forget who.
Yeah, it was me.
Okay, did you take it with China?
Yeah, I took it.
Okay, all right, cool. All right, so yeah, so hopefully she'll go over like the quiz stuff during recitation tomorrow. If you have any questions, I'll put up the solutions probably tonight after I finish grading your quizzes. All right, let's go through our agenda for today. There was something last class I didn't really touch on, something called conditional convergence that is important when it comes to alternating series and stuff. So I have to touch on that a little bit. There's another thing that I kind of didn't directly mention, but it's something that you should kind of be familiar with. So something called like knowing like your growth rates. My dog is like sleeping, and like she's like whimpering like while sleeping. You know what I mean? Like,
Show us proof where it didn't
no,
happen.
it's fine. It's okay. All right. So and then we're gonna review the test so far. Quiz 3, that is on the 28th. That is next Tuesday. Yeah. Quiz 3 is gonna be your redemption time. Okay. If you didn't do so hot on quiz 2, quiz 3 is gonna be the one that you can kind of like redeem yourself, because it's pretty much gonna have all the tests on it, right? all the tests that, because we're going to finish up the tests today with ratio test, and then a little bit of power series on there. Okay, so don't worry, there's no sequences on there. It's just straight up series, how to test the series, and then how to like deal with a power series. That's going to be next Tuesday. Okay, the final is that Thursday, so it's going to include everything after power series. Also, we're going to talk about something called Maclaurin and Taylor series. I know I know it sounds a little scary, but yeah, they're okay. All right. And then homework 6 is due tomorrow. All right. Any questions before we get started?
So the quiz is on more about like quiz on 728. What is it about again, sir?
The quiz 3 is going to be on all of the series tests and a little bit of power series, which is what we're going to talk about on today, if we have time today and Friday.
Okay, thank you.
Anyone else? Yep. Anyone else? No? You guys ready? Okay. Let's do this. Oh shoot. Okay. Here we go. So there's a couple things I want to kind of talk about because we didn't really talk about it last class. I guess I just kind of forgot it. Remember when we were talking about absolute convergence, right? I said when you think of absolute convergence, you think of absolute value, right? So that was the whole like premise of it, which means we are dealing with negative and positive terms instead of just positive terms, right? One of the examples that I did was the alternating harmonic series. It was like that. From n equals 1 or 0, no, 1, sorry. From n equals 1 to infinity. And right, the terms look like, okay, so it starts positive, so it's like 1 and then minus 1/2 and then plus 1/3 and then, oh, that's supposed to be minus, and so on and so forth, right? So we see that the terms are alternating, right? And I'm going to use AST to see if this thing converges or diverges, right? So if I say, I'm going to label this a sub n, right? Just the 1 over n part, right? I'm going to say, since the limit as n goes to infinity of a sub n is equal to 0, and because remember, you need to say 2 things for AST. That was the first thing. And the second thing is, oh my gosh. Oh, a sub n is decreasing. Let's forget. We say by AST, the sum of -1 to the n plus 1, a sub n converges. Right, so you guys remember talking about this last class, right? With alternating series tests, with absolute convergence, stuff like that. So one thing I kind of forgot to say, you notice that without the alternator, so if I just look at this guy without the alternator, what can you tell me about this thing? You want to chime in?
Ln is approaching infinity.
Ln? Where's Ln coming from?
It's a harmonic series. So
I'm talking about this guy right here. Yeah.
it diverges.
Yeah. So this is the harmonic series, right? So you can just say it diverges. You can also say by P series, since P is 1, the series is divergent. Yes?
Yeah.
So what do we have here? What do we have here? Well, we have something that diverges without an alternator, but then with the alternator, it converges. Do you guys see that? So this actually has this thing that's happening. This has a special name. This is called being conditionally convergent. That's all conditional convergence means. It means that on the condition that you have an alternator, the series will converge. But as soon as you get rid of the alternator, the series will diverge. And there are more examples out there that do this. But when you're dealing with series with an alternator, you must state whether or not if it's conditionally convergent or absolutely convergent. Can you guys guess what absolutely convergent means?
When they both are like the same.
It's always converging. It doesn't like diverge at all,
Regardless of
regardless of its sign.
Okay, fine. Yeah, regardless of if there's an alternator or not. Right. So, for example, I think this was the first example. Maybe I did with you guys. It looked like this. N equals. I don't know. I don't remember if I did this one with you guys, but this one, right? If I once again, I'm going to call this a sub n, and I'm going to compare the two, right? If I look at this versus this with the alternator, sorry. Right? If I look at both cases, without the alternator and with the alternator, you're actually going to conclude that these both converge. Right? I think I was talking with Lamek too during last class, right? I was saying like that the sum of this is going to be greater than or equal, no, less than or equal to? No, greater than or equal to, no, yes, the sum of this guy with the alternator, sorry. Right? And since this, if this converges, right, what is it going to force the other one to do? Now you talk.
Also converge.
Thank you.
converge.
Yes, it's going to force this one to converge as too, right? So by that logic, right? By that logic, you can say for this guy, since, so this is going to be like my write-up portion, since the sum of, I guess I should, hold on. I guess I should label it something else, right? I'm gonna label the series with the alternator something else, like this. I'm gonna be like, this is B sub n. Does that make sense? So I'm gonna go, since the absolute value of this, right, converges by P series, since like 2 is greater than 1, by P series, we can say that the sum of just without the alternator
It also converges.
converges, we're going to use a word called absolutely. Oh, what? I selected highlight. Go away. Oh my gosh. My computer. All right, there we go. Converges.
Wait, John, I have a question.
Yes.
So if the sum of if the sum of a sub n is convergent and the sum of the absolute value of a sub n is convergent, then it would be absolutely convergent.
So here's
yeah.
the thing. You only need to show that this is convergent. You don't need to check the other one. You know what I mean? Like you get the other one for free if you just prove the absolute value convergence.
Okay.
Right? And all you have to do is at the end just tack on absolutely in your write-up.
Okay.
Does that make sense?
Yeah.
Okay. So once again, we need to understand the difference between conditionally convergent and absolutely convergent because they are different scenarios, right? Once again, conditional convergence is when without the alternator, the series diverges, but then with the alternator, the series converges. That's conditional because it's on the condition that there's an alternator. But then absolute convergence is when it doesn't matter if there's an alternator on it or not, right? If the piece without the alternator converges, then you know that with the alternator, it will converge also. How's that?
John, can you just move to the right a little bit?
Like to the right? No, I'm just kidding. Okay.
All right, that's good. Thank you.
Any questions on conditional versus absolute convergence?
Two things real
Yes.
quick. For absolute, you said that whether it has an alternator or not, it always converges.
Yes. Right.
Like for that to be true.
Yes. Right. So if you just remove the alternator, what does that do to all the terms? It makes them all positive, right?
Yeah.
So if you remove the alternator and it converges, then with the alternator, it should still converge too.
Okay, and absolute is only in the case of when it's converging. Like, there's never a case where they both diverge, if that makes sense.
Right. There's no such thing as like diverging absolutely. If something diverges, it diverges. Like it doesn't,
Gotcha.
we don't really care about
Yeah.
absolutely.
And then the other question I had was, when you have an alternator, is it just -1 to the n power, or is it -1?
Okay. Oh, good question. Good question. Okay. It depends. So sometimes, you know, the -1 to the n+1, it'll be -1 to the n+1. Sometimes it'll be like a shift so that, you know, like the other half of the terms are negative. You know what I mean? Like,
Okay.
either it'll start on a negative or the
Or
second
it'll-
term will be negative.
Negative. Okay.
You know what I mean?
So that's what makes it different, like the.
Yeah. And then there are actually some tricky. You guys saw this on quiz 2, but there are some tricky alternators out there. Here's an example of one. That's an alternator. I know it doesn't look like an alternator. I'm going to call this a disguised alternator. I know it doesn't look like an alternator because it's not -1 to the n, but if you start plugging in n values, you see that
You get opposites.
you're going to get, if I plug in like 0, I get cosine of 0, which is 1. And then if I plug in 1, I get pi, right? So cosine of pi is -1.
Yeah.
Then you see it just flips back and forth between 1 and -1. So there are, you know, you can think of the sine one too, right? There's going to be I think a sine of, what is it, pi over 2 n?
I think in 3.
Yeah.
Yeah.
Every pi over 2 and to 3 pi over 2. Yeah, so there are disguised alternators out there, so just look out for them, okay?
Wait, so can you do like what if it was like you know how the problem above how you started it? What if it was n+2 instead of n+1?
Like up here?
Yeah.
So, well, think about it, right? Try plugging in 1, because we're still starting at 1. So that means it would be 3, right? So if -1 to the third power is
It's -1.
-1, right? So it starts
Yeah.
on a negative.
Okay.
This one starts on a positive, right? Because -1 to the second power is
The positive one.
yeah. Anyone else? Going once, going twice. All right, cool. Well, so that's down. What did I say I was going to do next? So we did, we talked about conditional absolute, order of growth rates. Now, so this is something, growth rates, something I should have really said, I guess in the beginning with sequences and stuff, but I mean, it's better late than never. It's important to understand which functions like grow faster than other functions. Wait, did that make sense? Yes. So there's like an order of like growth rates, like like what beats the other one, you know, in terms of like, you know, speed and how fast something grows, right? Like, so I'm just gonna give this to you so that you have, all right, it goes in this order. And then n to some power times ln of n, and then n to some power, yeah, okay. And then a to the n, and then, okay, this guy, which not a lot of you know, and that one. Okay, so what I'm saying, what this is saying here is, ln of n is the slowest growing function, right? And then as soon as you multiply n to some power to ln of n, that one's going to grow faster than ln of n. Does that make sense? And then as soon as you just have a power function, I guess they do this where it's like if it's something greater, like if it's something p plus another number, that's going to grow faster than n times ln of n. And then a to the n, which is an exponential, right? Like 5 to the x power, right? That's going to grow faster than a polynomial, right? And then this is called a factorial. We're going to talk about this today a little bit more. But factorials grow faster than exponentials. And then n being raised to an n, so that's 1 to the 1, 2 to the 2, 3 to the 3, 4 to the 4, 5 to the 5, 6 to the 6. That's going to grow the fastest out of all of these. It's important to know what grows faster than what, because when you take limits of stuff, right, If the bottom grows faster than the top, you know it goes to 0. If the top grows faster than the bottom, you know it goes to infinity. So this is kind of like a core idea that maybe you guys kind of like knew, but like was never really explicitly taught. You know what I mean?
John, I have a question.
Yeah.
What's the n p plus s again?
So this just means it's like a polynomial function, right? It's a polynomial so polynomial functions will grow faster than a polynomial function times a ln.
Okay.
If this power is bigger than this power.
Yeah. Okay.
Anyone else? Let me define factorial real quick. If you're not familiar with factorials, it just means n times n minus 1. It's a bunch of multiplication things. Some n minus 2 times ... You go all the way down to 1. So if I had something like 5 factorial, that's the same thing as 5 times 4 times 3 times 2 times 1. And you can imagine that these grow pretty fast, right? Like 1 factorial is just 1. And then when you hit like 3 or 4 factorial, it's 12 times 2, which is 24. You know what I mean? So factorial grows really fast, even faster than exponential. Any questions on growth rates? That's going to come back very soon. Okay. All right. I think we're ready for our last test. We are in section 10.5. They're called the ratio and the root test. Now, we're going to talk about the ratio test mostly. I'm going to mention the root test, but it's, some professors teach it. Some professors actually don't teach root test. It's up to you. It's kind of like the rules for both are very similar. The in-between step is just slightly different. So let me talk about the ratio test, all right? I just coughed right into the mic. I'm so sorry, guys. So we're on page 591. And here we go. Ready? This is not a P. It looks like a P. This is it's a Greek letter. It's called rho. It's a lowercase, it's the lowercase Greek alphabet, right? So rho is equal to, it's supposed to be like rounded, like, I don't know, you look it up, right? But it's equal to limit as n goes to infinity of a sub n plus 1 over a sub n. Ratio test, by the way, is like one of my favorites because it's so easy to use, and it's like, I love it so much, and you guys are gonna love it too. All right. So you're basically taking the limit of a sub n plus 1 over a sub n, given like some series, right? So yes, you can do this on any series, but there are 3 outcomes, 3 possible outcomes that you can get. All right, ready? So here's the first outcome. If rho is less than 1, then you can say this converges absolutely, right? So if the ratio is less than 1, because this is the ratio test. I don't know if I said that part. This is the ratio test, sorry. So if the ratio is less than 1, then you know that the series will converge. And in fact, you know it converges absolutely. The second case is if rho is greater than 1. That means the series will diverge. Once again, there's no such thing as diverging absolutely. If something diverges, it just diverges. The last case, if rho is equal to 1. I just drew rho like 3 different times. It's crazy. So if rho is equal to 1, then the test is inconclusive. So yes, there's a chance that the ratio test will not work, which means you have to use something else. Okay, but I'm going to give you a tip, a big pro tip. Ready? Pro tip. If you see factorials or n being raised to the n, so the last 2 growth rates, anywhere in your series, use the ratio test. Huge giveaway. Huge giveaway. So as soon as you see, by the way, it's not an exclamation point, so it's not like 5, right? So don't, or like n, right? So don't say it like that. People will mock you, right? So, but yeah, if you see the exclamation point, factorial or n to the n, use ratio test. It's a dead giveaway. Don't even bother doing the divergence test. Don't even bother doing any of the other stuff. I mean, okay, no, I lied. Do the divergence test. Always do divergence test first, but don't do, you don't have to do DCT. You can't use LCT. You can't use any of the other stuff. As soon as you see these two things, use ratio test. Sound good? Okay, let me kind of unpack the ratio test a little bit, because I know a lot of your like computers, when it comes to like doing math, it's like, oh, it needs to look like blah blah blah. But I want you guys once again to understand like what's happening here. Okay, so we're given a series. Okay, what am I doing here? What exactly is this action that we're doing here? Why am I taking a limit of a sub n plus 1 and putting it over n? And why isn't it flipped? Why am I not doing it backwards? Why isn't it a sub n over n plus 1?
To show that it's constantly decreasing.
Ooh,
That way
ooh, Alvaro, man, oh gosh. Can you say that one more time?
to show that it constantly decreases.
Okay, so
Like the
partially right. But we learned, or hopefully you guys know, or learned from the other tests, that just because it's decreasing does not mean it's going to converge. Like, for example, 1 over n, right? 1 over n decreases, but that's not going to converge. That actually diverges, doesn't it? What the ratio test is doing is kind of doing that. It is saying that, yes, we have to check for decreasing, but we are looking at, I'm just going to say, because I'm short on time, we are actually looking at the growth rate of the sequence and comparing it with itself from term to term, right? I'm taking the next term, a sub n plus 1, right? And putting it over the one right before it. You guys see that? And I'm letting those two things go to infinity. If that thing is less than 1, that means, yeah, the growth rates are, what's the word? Are shrinking enough for this thing to converge. Does that make sense? Right? If I had, and then if it's greater than 1, that means it's going to be increasing until you get to infinity and diverge off to infinity. That means it's growing too fast. Does that make sense?
So it's sort of like DCT, but comparing the series with itself, right?
You mean LCT?
Well, I mean LCT, yeah.
Yeah. I would, yeah, you know what? It's kind of like that. It is kind of like LCT, because it's just, you're not comparing with something that's known. You're just comparing it with itself and then letting it go off to infinity and seeing what happens, right? So, and the reason why 1 is inconclusive, right, is because, well, if I have like, I don't know, I can't think of something, like if I had like something like this, if this was my series, 1 to the n, right? What's the ratio of 1 to 1? Well, that's 1, right? And then this thing's going to diverge. But like, because it's 1, you don't know if it's going to diverge or converge, So like, if you get a ratio of 1, that means the terms are like, they're doing the same thing, like this versus this. Like, this one's going to converge, but this one's going to diverge. You see that? Like the rate between like the sum of 0 and the sum of 0, yeah, that rate is 1 because it's not changing, right? But then the rate of 1 to the n, that's going to go off when you add up 1 in an infinite amount of times. It's going to go off to infinity. Does this make sense? Kind of, sort of. Okay. If you didn't like any of that, it's fine. We'll just do an example, and then you guys are going to be like, "Oh, this is so easy. We should have learned this first." Right, so why don't we just do example 1? Oh, oh my gosh, I can't believe I just did that. I just did this. I'm sorry. Example 1. It says prove that this is convergent, and this is going to be good because it's going to give you some practice with some factorials, and I know factorials are a little tricky in the beginning. Okay, so definitely take note. So here we go. I see the factorial and I see the something raised to the n, right? So I know I have to use ratio test. Sound good? So let's do it. Let's do the ratio test. So I'm going to take the limit as n goes to infinity. So I'm going to, for this first example, I'm going to really write everything out so you guys see where everything's coming from, okay? So I'm going to take the limit, and I'm going to put absolute value signs on it because I want to show if it proves, I mean, if it converges absolutely, then it'll converge like regardless, right? So here we go. I'm going to do a sub n plus 1 over a sub n. And this is my a sub n. So I'm just going to rewrite this guy. Rewriting my limits. You know who I'm talking to. All right. So I'm going to rewrite this as an n plus 1 term over an n term. So what that means is I'm going to plug in n plus 1 for my n's, right? So I get 2 to the n plus 1 over a to the, oh my gosh, n plus 1 quantity factorial. This is my a sub n plus 1 term. I should have written it smaller. All over 2 to the n over n factorial. What the heck? This thing is possessed.
Wait, John, you chose your a sub n as which of the functions has the greatest growth rate?
No. This whole thing is a sub n. The sequence part is a sub n.
Oh, okay.
Yep. And then I just plugged in n plus 1 and put that over n. Sound good?
Yep.
Anyone else confused? Let me know if I'm going too fast. Okay. So I can rewrite this now. You guys learned keep, change, flip. Right? You know what I'm talking about? So 2 to the n plus 1 over n plus 1 factorial. I'm going to keep the top, change the bottom. Wait, no. I'll change the division sign into multiplication and then flip the denominator, right? So this becomes n factorial over 2 to the n. Eventually, you're going to do enough of these where you can just kind of like go straight to like this step, right? Because it's going to be pretty easy. These problems are easy, right? So this becomes this, right? And then, and we can kind of cancel stuff out, all right? So I hope you know your exponent rules well, all right? The top piece, 2 to the n plus 1, is the same thing as 2 to the n times 2, isn't it? Right? Because it's 2 to the n times 2 to the 1. I'm just doing the exponent rule backwards, right? So what does that mean? That means I can cancel out stuff. I can cancel this 2 to the n out with that 2 to the n, leaving me with just a 2 on top. Is Lamech here? Oh my gosh, it's been awfully quiet. Is he here? Oh, he's here. He's just really quiet today.
Yeah, I'm here.
Ah, there he is. I gotta hear your voice every class, man. It's just
Yeah,
embedded in
I'm
you.
sorry.
Okay. With the factorials now. So I'm gonna do the factorials off to the side because I want to be real explicit. Because when these start to get harder, like you're gonna be dealing with like 2n plus 4 factorial and n plus 1 factorial. You know, you got to learn how to like cancel these out. So I'm gonna do this a little bit more explicitly onto the right. So what we're left with is this: n factorial over n plus 1 factorial. What does that mean? Well, using the definition of factorials, n factorial is the same thing as n times the subtract 1 from n, right? So it's n minus 1 times the next one, n minus 2, times so on and so forth until you go all the way down to 1, right? If I write it out for the denominator, I get n plus 1 times n minus 1 times n minus 2 times so on and so forth until you get to 1. Do you guys see what's going to happen? Anyone? No? Maybe?
Everything cancels
Yeah.
out.
Not everything.
Factorial
But
cancel
the n
out.
plus 1.
Like that's n plus 1.
Yeah. Okay. So the n, that's gonna kill that. That's gonna kill that. That's gonna kill that. That's gonna kill that. That's all that's gonna, whatever, right? All that's gonna go away except for the n plus 1 on the bottom. Is that clear? So when the problems get trickier, like kind of like 2n, I don't know, I'm just making this up. factorial over like n plus 3 factorial, you have to know, like, just write it out. Don't be afraid to write. Don't do this all in your head, right? This is going to be like 2n plus 1 times 2n, 2n, and then I'll change this to 2n, and then like 2n minus 1, and like don't be afraid to write out your terms, okay? Because you need to know what exactly is left over at the end. Yeah. So I mean, if you want to try that later in your own time, you can. So going back to our problem, what does that mean? The n factorial is going to essentially get rid of that factorial sign, and you're left with 2 over n plus 1. I got a pretty easy limit here, don't I? Right? The bottom's going to go to infinity. So my limit is 0. You right there, Carlos? Okay.
I got it right, my bad.
Oh, I thought you were like talking to someone. All right. So so what did we just do? Remember, this is that rho symbol, right? This is the value of rho. And this is saying that when you go off to infinity, the terms are going to shrink down at a rate of 0, which means eventually, yes, the series will converge, right? So we say 0 is less than 1, or I guess rho is less than 1. So the sum of, oh my gosh, should I label it? Labels are important. Labels are important. I did a sub n, right? So I can just say the sum of a sub n converges. And how do I know? What test did I use?
Yeah,
Ratio test.
Thank you. See, you guys didn't do that on the quiz, right? Or a lot of you didn't do that on the quiz. You didn't tell me what test you used. You just said it converged or diverged. You know, like you gotta be explicit, right? So let me kind of recap here, right? The work only looks like a lot right now because I was very explicit. If you just show me this right here, that's enough for your work and write-up. So these problems are relatively fast. Yeah? Okay. Any questions on this example? We're going to do a harder one next. No? All right. So let's do, I don't know. Okay. So, oh my gosh, I did it again. Got math on the mind. Example, let's do, I'm gonna do like a variant of example 3. This is on page 592.
Example 3 looks hard.
Does it though?
I don't know. There's like 1,000 to the nth power.
So what? Okay, so I want to know, does this thing converge or diverge? I see the factorial. I see another to the end, so I know I have to use ratio test again, right? So here we go. I'm going to be a little faster on this one, so let me know if I'm going too fast here. I'm going to set up my limit, and I'm going to plug in the n plus 1 term. Now, I can ignore the -1 to the n. Why? Because we're checking for absolute convergence. You see that, right? In the original definition of the ratio test, there are absolute value signs. So I can kind of ignore the alternator, all right? So here we go. I'm going to plug in n plus 1. And right away, I'm going to do the keep change flip. So it's going to be 1,000 to the n over n factorial. Now is the cancellation step, right? See what cancels out. Well, we just kind of did this one on the last one, right? So I'm not going to explain that again. That's going to cancel out with that. And, oops, and this is going to cancel out with that, right? Leaving me with n plus 1 over 1,000. What's going to happen?
It diverges. It approaches infinity.
This is greater than 1. Our rho value, our limit is greater than 1. So by ratio test, the series diverges. Done.
John, instead of saying like the series, like if we labeled it, we could just put sum, whatever.
Right? Any questions on this one? They do get crazier. I'm just letting you know. Mohammed, what's up?
Yeah, no, I was gonna say that looks a lot easier than the other one.
Like I said, this is a crowd favorite because they're like really fast and easy to do. Let me do one more example. Oh my gosh, what is wrong with me? Okay, this is example 4. We're gonna look at, I guess, this one. Now, let's say I was just not feeling it that day and I didn't want to run divergence test, right? Actually, you know what? I think this one will
Kind
be
of tells
better.
us the answer.
I know, yeah, I know. I'm telling you
Yeah.
the answer right away, right? Like, okay, so I'll do this one then. So let's say I wasn't feeling the P series test for some reason, right? And I'm like, I don't want to use that one. I'm going to use ratio test because I'm feeling, whatever. I'm feeling spry, right? So I'm going to use the ratio test. What the freak? This thing's possessed. I'm going to use the ratio test. So I set up my limit like normal, absolute value. So this is going to be 1 over n plus 1 squared over 1 over n squared. Yes. Yeah. Which is the same thing as n squared over n plus 1 squared. Right? Maybe you guys can see it. What's going to happen? The power on the top is the same exact as the power on the bottom. You're going to get 1. So what does that mean?
It's just inclusive, yeah.
It means you did all that work for nothing. I mean, granted, it wasn't that much work, but like it was
That's
like,
all we have to do if like it was that kind of problem. That's all we have to show. That's it.
Yeah.
Okay.
So, but the thing is, your result is inconclusive. So you're not done with the problem. You can't tell me convergence or divergence yet, right? So you would be like, oh, silly me. I should have used the P series test and been like, because this is the same thing as 1 over n squared. So this converges by P series, right? But you guys are budding pros at this, so like you're not gonna make that mistake. I just wanted to show you an inconclusive example. So, and usually the inconclusive examples happen with like n to some power, right? And that should kind of make sense because we already know how to deal with n to some power. That's with DCT and LCT or P series, integral test. Like those are the tests that we should be using, not ratio test. Ratio test is mainly for the factorials and n to the n power. Okay. Now, and that's it. That's ratio test. There are probably harder problems out there that China will probably assign for you guys, but yeah, definitely get good with using the ratio test. We're going to need it for the power series part. Now, I'm going to just talk about it, but this is not required for my class. There's something called the root test. And you use when you see n to the n, something being raised to the n power. You don't really use it as much with the factorial, but the 3 outcomes are the same, and the reasoning should be very similar too. So you're still taking the limit. It's just now you're doing the nth root of your sequence. And that should kind of make sense, right? Because if your sequence has something to the n and you nth root it, they'll cancel each other out, right? So they're still absolute value signs. And the 3 outcomes are the same. If this is going to equal rho, if rho is less than 1, it converges. If and so on. I'm just lazy. I don't want to write the rest. Okay, just the root test. Don't worry about it for me. In the fall, your professors might do it. If rho is greater than 1, diverges. If rho is 1, it's inconclusive. Okay. Any questions on ratio tests? No. I don't know. We actually have some time. Do you guys want to do one more ratio test problem, like a harder one, or do you guys want to move on? I'll leave it up to you. This is your chance to speak.
Can we do a harder one?
Yes. That's what I was hoping you guys say. Let's do. I'm gonna jump down to the exercises. Let's do. No, that was easy. Oh, I know where to look. No, these ones aren't that bad either. Okay, fine. I don't know. I can't really find a really good one here. Let's look at n factorial over 2n factorial. Get you guys some exposure to these factorials. So come on, buddy. There you go. All right. So thoughts, like walk me through this. Like, what are you guys thinking? What do we do first?
Ratio test.
What do we do before that?
We set up the limit and stuff.
What test do we always do first?
Divergence.
Oh, divergence test.
Always, or in your mind. You don't have to put it on paper. I'm not asking you to put it on paper. This is something you do with every series you come across. Always run divergence test first. Okay. For this one though, it's kind of hard to tell because n factorial over 2n factorial. This is the same thing as what is it? N times n minus 1 times n minus 2 dot dot dot, and then this is 2n. 2n minus 1, 2n minus 2. And it's kind of hard to tell. I would say, wait, I think this diverges, right?
John, if you do the limit as it goes to infinity for the divergence test, wouldn't it be indeterminate?
No,
Yeah.
this is because like this n will cancel out with that n. This power cancels out with that power. The amount of n's are like the same. So I think this is actually going to be like 1/2.
Oh, because the 2.
Huh. Okay. Wow. We just proved this without the ratio test. Okay. Dang it. I told you guys this wasn't a good problem because it's not hard enough. Okay. Ooh. Here we go. All right. I got a better one. E to the n over n factorial. Haha. This was good. So sorry, I didn't finish this last problem. Diverges by divergence test. Boom. Okay. Next one. So we do the divergence test on this one, right? And this is going back to what I was saying about those growth rates. Do you remember what I said about those growth rates? What grows faster than what? No? Maybe?
Doesn't the factorial grow factor? I mean, the factorial
Yes.
grow more than.
Factorial grows faster than e to the n. So this is actually going to go to 0. This fails the divergence test, so we got to use something else, right? So this should be the thought process when you're coming across a problem, right? So I have to use the ratio test. Also, like I said, you see the factorials, you see the e to the n, yeah, you're going to use ratio test. Okay. So I set it up. This is going to be the limit as n goes to infinity, absolute value. I plug in n plus 1. So replace all the n's with n plus 1. So this becomes e to the n plus 1 over n plus 1 quantity factorial. Please do not do, I don't know why you would, but like don't write it like this. Why don't you want to write it like that?
Because
Only the 1 is being.
factorial.
Yeah. So you got to watch those parentheses, okay? Please, this is a no-no, okay? That's a no-no. Handel, don't do it, okay? I'm looking at you.
Oh,
All right.
I will.
Oh, I forgot something. So we plugged in our n plus 1 term. Now we times the flipped n term. Did that make sense? The flipped n term, right? So this becomes n factorial over e to the n. Oh my gosh. And we simplify. This one's not that bad either. Dang, I was hoping for like a 2n plus something. Those are fun. But yeah, okay, so hopefully you guys can see, right? What's gonna happen with the n factorials?
It's just 1 over n plus 1.
Yeah, so the n factorial is gonna get rid of that factorial. E to the n is gonna kill this guy. And you're left with e over n plus 1. And what is e? Because so many of you don't apparently know what e is from quiz 2. Do you guys know what e is?
It's like
The natural number.
The number's like
something.
2.71.
2 point.
Yeah, it's like
yeah.
2.7.
It's 2.71828 something.
Such a
It's an
number.
irrational number, but it is a constant, okay? It's a constant. It is not a variable. We're not taking e to go to infinity. That makes no sense, right? So this is 0, which is less than 1. So since rho is less than 1, you better answer it. The series, wow, blowing up over there, converges by the ratio test. Easy peasy.
Were there any problems on the quiz we could have used this to do? Just curious. What do you think?
No, I don't think so. Either you could have done it, but it probably wouldn't have been the most efficient testing
Way to do it? Okay.
All right. So yeah, that's ratio test. I'm actually I'm gonna share something with you guys. So I put it in the whatchamacallit, the files
file
section.
thing.
Oh, did you guys see it already?
Yeah, I saw that. Like, I got a notification. You did like the flowchart, right?
Oh, you guys get notifications on that. I did not know that.
Yeah.
Okay, cool. So can you guys see my screen? Oh, I didn't share my screen. Can you guys see my screen now?
Yeah.
So I gave you guys a handy dandy flowchart. It goes through all the tests and then some, right? It even talks about telescoping series, which, like I said, I'm not really going to deal with, but you know, it's just there. Taylor series, we won't talk about that yet. We'll talk about that in a couple classes, okay? So don't worry about Taylor series right now. But it goes through everything, right? So once again, you start with divergence test, right? Can you guys see my mouse? Does my mouse come up?
Yeah.
Oh,
Yeah.
sweet. So you test for divergence first. Is the limit 0? No, then it's divergent. Boom, you're done. If it is 0, you have to pick another series. They go to P series next. Not my choice, but you know, whatever. Right? Does it resemble this? Is it, you know, does it fit the criteria? If so, blah, blah, blah. If it doesn't, check if it's geometric. Is it geometric? You should know what to do. Does it have an alternator on it? Right? If so, does it fit the 2 criteria? Then you can say convergent. Telescoping, I'll skip. Taylor, I'll skip. Comparison test. Pick a B sub n, right? So in this case, they're saying B sub n is the known and A sub n is the unknown, right? And then they go through the criteria. So this comparison test is the direct comparison test that we learned. Then they say if you can't do this, you go to limit comparison, right? You take the limit, see what happens, blah, blah, blah. If none of that works, then you go to integral, I guess. If it looks like a function that's continuous, positive, decreasing, yada, yada. If you can't use integral, try ratio or root. Yeah? So it's a pretty useful tool. I don't know. My kids usually, not my kids, like my students usually like this flowchart. They say it helps them a lot. So yeah, definitely use it especially for the next quiz. In addition, the second page, there's a bunch of problems. I'm not telling you to do them all. I'm telling you to try some of them or even look at some of them and just think, what would I do? For example, like, I don't know, number 20. If I'm looking at number 20, I see a 5 to the k on the bottom. Pretend they're n's if you don't have the k's. Can you, just gonna mute you. I see the 5 to the k on bottom, right? So something's being raised to the k. So what am I thinking? What test am I thinking of here?
Do GCT?
Because DCT would mean I would need I would need to know what happens with k over 5 to the k, and I don't know what happens to that without doing some more work. What's the easiest test to use here? What did I say? When you see
Divergence
something
test. Oh, never mind.
after divergence test, because it's gonna fail the divergence test. But I see
Yeah.
5 to the k. I see something being raised to the n power. We just learned this.
I do.
Would you
I
do
do
ratio test?
Oh,
Ratio
yeah.
test. Ratio test. The Horatio test. Right. It's 5 to the n or k. So immediately that tells me I need to use ratio test. Okay. What about number 11? What do you guys think? What are thoughts? It's gonna fail the divergence test, so that's out the window. What test would I use next?
Alternating series.
Yeah, AST.
Some sort of alternating series test, okay. But I also see 1 over n times ln of n. Does that pop out to anyone? This one's kind of tricky.
Integral?
Yeah, this is an integral test because I see a u sub that I can do
Yeah.
there, right? I know that one was kind of tricky.
What about 24?
24? Where's
Yeah,
24?
the
24.
cosine.
Oh yeah, okay, cosine, this guy, yeah. So what would you guys do for that one?
Could you? Can't you use the comparison test because of cosine?
I would use a comparison test. I would probably use the limit comparison test for that one because the cosine, cosine's bounded between 1 and -1, right?
Yeah.
So, I would maybe use some sort of that, like, try to get it to converge on top because I see n squared on the bottom and I know n squared is convergent, right? So this one would probably be a LCT and compare it to 1 over n squared.
Yep.
But do you guys see the thought process here? Do you guys see how I'm like thinking, like approaching these problems, right? Number 16, oh my gosh, dead giveaway. Like what would you do for number 16?
DCT.
A DC, it might have to be LCT, I'm not sure. I would have to check, but yes, it's a comparison test, right? I see n squared on top, n cubed on bottom. So I compare this to 1 over n, right?
Yes, sir.
Do you guys see what I'm saying?
Makes sense.
Yeah.
So
yeah.
definitely, take some time, go through some of those problems, and yeah, I mean at your leisure, of course. Dang, I was hoping I could start power series, but I guess you know what? I'm just gonna briefly start power series just because I really wanted to today, and I know you guys are really cool and will let me do that with no rolling your eyes or anything. So power series, let me just explain what they are. I'm not even going to go into, we're not going to do a problem. I'm not even going to go into like the notation or anything like that. I just want to explain what a power series is, okay? So this is section 10.6, power series. So we've done all the tests. We went through all of the tests. So geometric, divergence, help me out here. Integral,
P series,
P series, thank you. DCT,
LCT, ratio,
AST, alternating series test, right?
Test.
integral.
I think I said integral already.
Okay.
And then did I say ratio?
I said I think I don't know.
Okay, ratio
Someone said
test. Okay.
ratio.
So along with conditional and absolute convergence, right? So we now have all of these tests. We have all of these tools to use, and we're gonna use them on power series a little bit. Okay. So what a power series is, okay? What a power series is, it is just a series. It's a series with one caveat. Okay. There's gonna be some sort of variable within your power series. Okay. And you're gonna see it's gonna look like this. Okay. I know it looks scary, but let me go through it. Okay. This part right here, you should know, right? We know how to deal with series, or we know how to deal with series now, right? Hopefully, after more practice, you guys will be better at that. I promise. We know how to deal with series, but what this does now, it kind of like opens up a new avenue for us in how to use these series. Think about it. If I'm throwing a variable in, x is my variable, this means I now have an input which can produce an output. What am I hinting at here?
Like a function type
Yes,
thing?
Yeah.
yes. We are now dealing with series that represent functions. I know. And what's
Wow.
crazy is with these functions, we can apply calculus to them. We can derive them. We can integrate them. We can take limits of them and do whatever we want with them, right? Like everything that we did from algebra up until calculus, we can do to these power series. There's just a couple of things that we have to kind of do first, right? So hopefully that kind of, I'm going to leave you guys off on that cliffhanger. Hopefully that for the next class, you guys will be like, oh, yay, I can't wait to learn about power series, right? Yeah, I know you guys are excited. All right. So
fun.
tomorrow, homework 6 is due. All right. Don't forget your quiz 3 is going to be next Tuesday. Know your dates. If you guys want to stick around, ask any questions for any of the tests. Oh, John, can you go over that one test real quick? By all means, I'll be here for a little bit. But if not, you guys are free to go. I'll see you guys on Friday.
I'll see you, John. Have a good one.
See ya. You too.
Was that your little intro to Maclaurin and those type of series?
Yeah. So Maclaurin and Taylor series are specific
They work
power
as
series.
functions. Yeah,
They're
right.
very, very specific cases of power series. So yeah,
Yeah.
we're gonna get into all that. Don't worry.
I don't think I remember learning power series this school year.
I mean,
BC.
sometimes it kind of gets glossed over because Maclaurin and Taylor like are power
Yeah.
series, so they don't really explicitly say like power series, but it is important to know what a power series is. It's a function.
Yeah.
John, I have a question. If you have like e to the n within like your series,
Yeah.
is there a specific, I guess, indication from that alone that can give you what test to use, or does it just depend on the whole thing?
So some things being raised to the n, immediately I think of ratio test.
Okay, so if it's like
Remember, e is just a number. If it was 4 to the n, if it was 5 to the n, if it was 100 to the n power, I would still
same
use
thing.
ratio test. Yeah.
okay, if it was like, I think this was from the quiz, like n plus 1 over e to the n.
Then you just make
I
it
don't
n
think
plus
that was the
2.
problem. That one was the U sub problem. That was an integral test one.
Okay.
Yeah.
Gotcha. All right.
So I guess you didn't get that one right.
It was, man, it was at the end. I was like, you know what?
I know.
Just put stuff down and we'll see. I looked back at it. I was like, wow, I should have got this one right. It's cool though.
Yeah, I'll put up the solutions tonight, so be on the lookout for them.
Got you.